What happens if you just keep cutting in half? Let's start with an apple and a really, really sharp knife. You take the knife in your hand and with a flourish you slice the apple into 2 neat pieces. The apple halves become quarters, then the quarters become eighths. In front of you are smaller and smaller pieces of pulpy white apple. But by your 14th cut, a regular rectangular pattern emerges and you realize the smooth apple flesh is built out of an array of plant cells. You keep on cutting, chopping the cells into smaller and smaller pieces. Another 8 cuts reduces the cells into complex molecules of carbon, hydrogen and oxygen. And with a few more cuts, what was once the apple is now 10 to the power of 27 individual atoms. Is this it? Can you cut no more? But your knife is incredibly sharp, and you begin to chop into the atom. Peeling away the cloud of electrons, you reveal the seeming nothingness within. Almost nothingness, for at the center sits the tiny atomic nucleus, 100 trillion times smaller than the apple that you started with. But again you are undaunted, and again you continue chopping. The nucleus splits into protons and neutrons, the protons and neutrons into quarks and gluons, and you find yourself in the ethereal world of the subatomic, a world governed by fuzzy probabilities, the apple now nothing but an ethereal wave upon a sea of fields. It feels like you have finally reached the limit, the fundamental pieces of the universe. Though some think you can keep going. After more than 100 cuts, point-like quarks and electrons might be revealed to be waving strings, barely a trillionth of a trillionth of a trillionth of a meter across, vibrating across extra dimensions. Down here, maybe even space and time are chunky, fundamental blocks that can be cut no more. Or maybe any semblance of reality will melt away, as we find that our universe is truly a simulated cosmos, churning away on some super-dimensional computer. Or that our 3-dimensional existence is nothing but an illusion, and everything we know and love is shown to be a hologram. Or even more strangely, maybe it's just raw mathematics, all the way down. But which is true? And how can we be sure? To understand reality, the true nature of reality, and how humans over thousands of years have struggled to unravel it, we are going to have to dissect the cosmos and ask some very difficult questions. Is the apple real? You can hold it, smell it, taste it. You can see the greenness of its skin in the sunlight. Surely the apple is real. But what does it mean to be real? Just what is reality? Isaac Newton used to bookmark the pages in his books in a very specific way. He would turn the corner of the page down onto the phrase or even the word he wanted to remember. Of course, it was easy for him to concentrate, as he had no mobile phone determined to distract him or suck him into endless doom scrolling. And so our sponsor today is the perfect learning tool for our modern age. If you care about building a life of learning, Imprint is the app for you. If you haven't used it before, you probably haven't seen anything like it. It provides bite-sized lessons that take only a few minutes and are beautifully illustrated and animated, creating a highly visual, effective and interactive learning experience. Their library includes courses, book summaries and quick-read articles on topics like psychology, philosophy, physics, productivity, science, history and many more. I personally have been enjoying Carlo Rovelli's dive into the mind-bending physics of time. And another exciting option I've been looking through is Thinking Fast and Slow by Daniel Kahneman, which helped me understand my own cognitive biases. And so now is a great time to try everything Imprint has to offer, free for a full 7 days, by scanning the QR code, visiting imprintapp.com/universe, or clicking on the link in the description. Plus, as fans of the entire history of the universe, you'll get 20% off Imprint's premium subscription. To our truly ancient ancestors, reality must have been obvious. From the plains of Africa to those wandering the snowy wastes of northern Europe, reality was what you sensed with your eyes and ears, touch and tongue. Reality was simply out there. The snap of a twig in a forest might tell them that their next meal is at hand, or warn them that they might be on the menu for a beast with bigger teeth and sharper claws. Sensing reality was a matter of life or death. Perhaps therefore, in their day-to-day struggles, these truly distant ancestors had little time to wander, little time to think deeply about the world that surrounded them. But as the human mind developed and thoughts expanded, the nature of reality surely changed as well. We know humans began to bury their dead almost 100,000 years ago. Quite what they were thinking as they bid farewell to their loved ones, we'll never know. But perhaps they were thinking of a world beyond our reality, an afterlife. These ceremonies provide insight into human thought, and that there was more to reality than meets the eye, or ear, or nose. Ideas around spirits and gods and invisible yet powerful influences began to emerge, along with questions of meaning and purpose. And of course, the gods also gave us the apple, providing delicious fruit for us to eat. There was no need to question the reality of the apple beyond this. The answer was simply beyond the ponderings of the human mind, only found in the thoughts of the gods. But others began to wonder more deeply. Plato was one of the greatest philosophers of the ancient world. Living in Athens in the 4th century BC, his real name was Aristocles, with Plato being just a nickname that meant broad and apparently referred to his stocky build. The material world bothered Plato. Where do objects get their material properties? Be it the greenness of the apple skin or the fact that dogs have 4 legs. Our world, Plato contended, was not the real world. And to understand this, we will have to explore his famous allegory of the cave. In this cave, a group of prisoners are kept chained, staring at a wall. The prisoners have always been there, chained in the cave, and have never been outside and experienced the real world. All the prisoners can see is the wall in the cave in front of them. But on the wall, they see shadows. These are formed by sunlight streaming into the cave entrance as people go about their daily business at the mouth of the cave. What are they to make of this external reality, one that they can barely see? How are they to understand the real world? But we can go further. What if they are not really seeing shadows of reality from beyond the mouth of the cave? What if, instead, some mischievous people have blocked off the cave entrance and are illuminating the prisoner's wall with a bright fire? With this light, these people can now play mind games with the prisoners, using shadow puppets to play out stories on the wall. No longer are the prisoners simply seeing people wander by the cave entrance. Now they can see stories of monsters and battles, castles and kings. What are the prisoners to make of this new reality? Is it any less real than before? To them, this image on the wall is their reality, there is nothing else. And so, these exciting new tales are as real as the previous shadow people milling about. To them, the monsters and battles are truly real. Plato then asks us to consider that we are like the prisoners, and the reality we experience every moment of the day is a projection of a place where true reality plays out, with our imperfect world being a shimmering image of perfection. To Plato, our experiences are just shadows of a true reality. Considering what we know now, this was oddly prescient. But for the story of reality, this was just the beginning. For to reveal the secrets of the universe, to unveil the ultimate truth of the nature of the cosmos, the answers did not lie in the hands of the gods or ancient philosophy. Instead, we would have to delve deep into the fundamental makeup of matter, time and space. We would have to turn to the insights into reality provided by scientific exploration. And when we did, things quickly got very strange indeed. Philosophy will clip an angel's wings, conquer all mysteries by rule and line, unweave a rainbow, In the first few months of 1821, the poet John Keats died in Rome. He was young, only 25, but his body was racked by the scourge of tuberculosis. In his short time, he was prodigious, writing on the natural beauty of the world around us, and like many before and after, he was only truly recognized after his death. Keats was born almost 70 years after the death of Isaac Newton. It was the time of the Industrial Revolution, a revolution driven by Newton's insights into the natural world. The scientific revolution of Newton and his contemporaries had sought to peel back reality and reveal it as nothing more than a manifestation of physical law in action. And finally, it had been Newton who had realized that the white light of the sun contained all the colors of the rainbow, and that water droplets in the sky spread sunlight in a glorious display from red to violet. The seemingly mystical appearance of one of nature's true wonders had, Keats complained, been destroyed by Newton, reducing it to little more than a prism. In Keats' words, Newton had tried to unweave the rainbow. Newton's triumph might have been Keats' lament, but as Newton began to unweave the nature of light, he kick-started a long tradition of science, peeling away the very nature of reality to expose its bones. Let's think again about our apple. Of course, one of the defining characteristics of a ripe apple is its colourful skin. But just where does this colour reside? Apples are made of a complicated mix of water, sugars, and more complex structures. So why do we see the apple appear green? To answer this question, we must delve deeper into the meaning of colour. And the story begins with the last man who knew everything. Thomas Young was born in the tiny Somerset town of Milverton in 1773. Precocious from the very start, he learned French, Greek, Italian, Latin, Aramaic, Persian, and more, and was instrumental in deciphering Egyptian hieroglyphics soon after the discovery of the Rosetta Stone. For some of you, Young's name might already be familiar, as it was Thomas Young who undertook the first of what's known as the double-slit experiments. We will return to Young's double-slit experiment later in our story. Artists knew that mixing coloured paints produced new colours, and three colours, red, green and blue, seemed to be particularly important. Young proposed that the eye contains three kinds of fibres we now call cone cells. One kind is sensitive to red, another to green, and another to blue. The amount that each kind of cell is stimulated is passed along the optic nerve into the brain, where it is mixed like paint in the mind to give us the sensation of colour. Things, however, get weird when we look at the eyes of other animals. Our closest relatives, apes and monkeys of the old world, are similar to us, sensitive to three colour bands, but most mammals only have two, equivalent to our blue and green. This must reduce their colour palette. Would they see a banana as being yellow? Bees have three colour receptors, one sensitive to blue, another to green, and yet another to ultraviolet. Reptiles, fish, and birds can have four or more colour receptors. Indeed, the small but violent mantis shrimp has a total of 12 receptors spread across the rainbow. These animals must see the world in an array of colours that we can't even begin to imagine. And so what are we to make from this confusing array of animal visions? For humans, the yellow of the rainbow matches the stimulated signal from the skin of a banana, but other creatures probably wouldn't agree. To them, maybe a strawberry or broccoli or human skin is the same colour as a banana. This tells us something deep about the nature of reality. Our sight is nothing but a shadow of reality created by our brains. It is subjective, not objective. We live in a visual simulation of our own making, built from stimulations being fed into our brains. Newton told us about raindrops and sunlight, but the colours of the rainbow only exist in our minds. The sounds that we hear are similarly illusions, an interpretation in our minds of vibrating eardrums due to waves of pressure in the air. We live in a virtual reality of our own making. So if what we perceive is not truly reality, then what is? Well, space and time can at least be trusted. The apple is here and now. That is one certainty. Or is it? For in the revolution that was to follow Newton and Young, no part of reality was safe. Time ticked by slower in the past than today. And in 2023, astronomers measured by just how much. Their focus was quasars from 12 billion years ago, black holes weighing billions of times the mass of the Sun. Swirling in the intense gravity of these black holes, matter orbits at close to the speed of light. This matter is heated to billions of degrees and glows intensely, visible across the universe. But in the turbulent maelstrom, before it vanishes into the hole, matter crashes and grinds, and the intense light brightens and fades like a cosmic firework display. Hidden in this flickering, astronomers found a subtle pattern, a special regularity, and they realized that they could use this quasar tick to measure the passage of time when the universe was young. These astronomers compared the tick of a clock today to the ticks of these quasars, finding that the farther away the quasar, the slower and slower these quasar ticks became. And when the universe was 1/10 of its present age, relative to today, time was ticking at 1/5 its current rate. This result was spectacular, but it was not unexpected. For this cosmic dilation was written into the mathematical laws that govern the universe, in a theory developed more than a century before, a theory that forever changed the reality of space and time. I think, therefore I am. It was the French philosopher René Descartes who uttered these famous words, and this deep musing on the reality of being has reverberated throughout the centuries. But Descartes stared into more than just the meaning of being. One night in 1619, Descartes shut himself away in a small room to avoid the cold. As a mercenary fighting for the Dutch Protestant state, he had studied engineering and mathematics. But this frigid night would be like no other. The story goes that Descartes was confined to his sickbed, staring aimlessly around the room. He spied a fly walking across the ceiling before launching into flight, darting about and settling on the wall. As the fly buzzed about from ceiling to wall and back again, a thought wandered across Descartes' mind. How could he describe the journey of the fly? He realized that he needed a reference point to anchor the motion of the fly. And while this point is arbitrary, he must be consistent and not change it. He also realized that talking about the distance from this point to the fly is simply not sufficient, because as well as the distance, you need the direction of the fly to fully describe its motion. Then a startling thought came to Descartes, a realization that would simplify the fly's motion. For his point of reference, Descartes took the corner of the room, where two walls met the ceiling. From this point, Descartes imagined lines running along the joins, defining axes that meet at the corner at right angles. If you project the fly's location onto each of these axes, Descartes reasoned, then you get numbers, and it's these three numbers that you need to specify the location of the fly at any instant. Three numbers to uniquely define a location in three-dimensional space. Three numbers that change continuously with the ticking of the clock. Descartes' coordinate system seems obvious to us today. Children are taught to use it when they encounter location and motion in elementary science. For professional scientists, laying down a Cartesian coordinate system is the start of finding solutions. And so Descartes' name continues to reverberate throughout the centuries. Dying in 1650, Descartes was unaware of a young boy growing up in the English countryside. This boy, Isaac Newton, would grow to use these notions of time and three-dimensional space, laying these down as the mathematical stage on which all motion takes place. It was Isaac Newton who laid out the rules that we now call classical mechanics. In Newton's universe, time is a true absolute. a single clock that ticks across the universe, a tick that everyone agrees on. Space was slightly more complicated, as Descartes' contemporary Galileo had discovered, as each observer has the freedom to define the origin of their own coordinate system. Galileo thought more in terms of stories than in the mathematics of Descartes or Newton, and he laid out his notions on motions in thinking about being on board a ship. He realized that if the ship was in a harbour or sailing smoothly on a glassy sea, then the experience below deck would be identical. However, if the wind picked up and the ship began to speed up, or if it sailed into choppy waters so the ship began to rock and roll, then those below deck would feel this change in motion, as plates and cutlery slide off tables and people become unsteady on their feet. From this, Galileo declared that there must be no absolute rest in the universe. All motion, he said, must be relative, and the laws of motion must be the same for observers in a state of unaccelerated motion. The first theory of relativity had arrived. These ideas are reflected in Newton's equations of classical mechanics. Every observer in uniform motion can use Newton's 3 laws to calculate the outcomes of experiments. It's easy to test this yourself by dropping a ball on a train station platform and seeing it fall to the floor. Repeat this experiment on a train travelling at uniform constant speed, and again, the ball will simply fall. If, however, you drop the ball at the start or end of the train journey, the train will be accelerating up to speed or slowing down as it approaches its destination, and dropping the ball at these times will see the ball veer towards the back or front of the train, seemingly defying Newton's laws as no forces are pushing in these directions. These fictitious forces only appear as your coordinate system is accelerating, and they vanish as soon as you achieve uniform motion. This picture of the background of reality existed for several centuries, until a Scottish physicist, James Clerk Maxwell, finally unravelled the mystery of light, and with it, the bizarre reality of our universe. Maxwell's impact on science was enormous. By the mid-1800s, Maxwell had mathematically united electricity and magnetism. There had been experimental clues that these strange phenomena were related, but in a handful of equations, Maxwell showed that these two things were one and the same. This was already an immense achievement, one for which Maxwell would become scientifically famous, but he looked deeper into his equations and realized that they implied something profound. He realized that light itself must be an electromagnetic phenomenon, oscillating and intertwined fields of electricity and magnetism. His equations also revealed the speed of light, a blistering 300,000 kilometers per second, but curiously, not what this speed is relative to. By just whose coordinates was this speed determined? It seemed that a notion of absolute rest would be needed to save physics. Some had proposed that there was an absolute background, an ether in which light propagated throughout the universe, and had been creating experiments to test the idea. This included experiments bouncing light rays off mirrors, or sending a current through an electrical circuit and lighting a bulb. The outcomes of these experiments would depend on the motion relative to the ether, and were built to demonstrate that the universe must possess an absolute state of rest. However, this would be a serious headache for Galileo's idea of relative motion. Why would electromagnetism know about this state of rest, while the rest of physics didn't seem to care? Why would Galileo's relativity hold for everything except electromagnetism? Why would the physics of reality have to be so complicated? In 1905, one physicist stated that it didn't have to be so messy, that the universe was not split into some physics that obeyed Galileo and some physics that didn't. No, electromagnetism had to respect relative motion also. And so, at the start of the 20th century, Albert Einstein's special theory of relativity was born. At its core, the special theory of relativity reflects the dream of the lazy physicist, the dream of explaining as much as possible with as little as possible. Einstein demanded that all observers, irrespective of the relative motion, can use Maxwell's equations to calculate the outcome of electromagnetic experiments. But this comes with an uncomfortable consequence, as all observers must measure an identical value for the speed of light, and this was simply not possible with Newton's notion of space and time. And so space and time, Einstein claimed, are not rigid or absolute. Instead, they must be flexible, such that times and distances depended on who is observing them. This sounds like lunacy. Indeed, this is not the experience of our everyday lives, but experiments close to the speed of light reveal this distortion of space and time. And it was in the 1960s that irrefutable evidence for the twisting of time was found. The focus was on a subatomic particle, known as a muon, effectively a heavier version of the electron. But unlike the electron, which lives forever, muons only last for 2/millionths of a second. After this, the muon disintegrates into electrons and neutrinos. Physicists knew that high-energy muons were made in the upper atmosphere, created when particles from deep space smash into the gas molecules. As they travel close to the speed of light, the muons should have traveled half a kilometer before decaying, but physicists detected muons arriving at the ground after traveling many tens of kilometers. Why were these muons lasting so much longer than their lifetime said they should? The answer, physicists realized, lay in Einstein's special theory of relativity, and, in particular, a quantity known as the Lorentz factor, a factor that dictates the dilation of time. To explore this, we must understand the immediate consequence that sprang from the special theory of relativity. The speed of light is an absolute speed limit to the universe. No matter how hard we try or how much energy we have available, no object with mass could ever get up to the speed of light. The Lorentz factor depends on the relative velocity, but as speeds get closer to that of light, the Lorentz grows unbounded. And so though for the muon its life is over in just 2/millionths of a second, for the physicists here on Earth, the muon's life appears much longer, and it makes it to the ground. Of course, there is a flip side to this story, the other side of Einstein's strange relativistic coin. The physicists see the long-lived muon travelling tens of kilometers before decaying, but if you could ask the muon, it would say it had only covered a few hundred meters in its short life. Space, as well as time, can be distorted and dilated when speeds get close to that of light. And Einstein also realized that this speed limit had profound implications for information, as this could also not be transmitted faster than light. A classic example of this is that we don't see the sun as it is now, but as it was 8 minutes ago, and the light we see from the Andromeda galaxy set off before humans walked the Earth. Through their telescopes, astronomers see galaxies as they were billions of years in the past. Indeed, the universe, as it is now, is completely hidden from us. We only spy as it was in the past, along what is known as our past light cone. The further an object is, the younger it appears. And other consequences from Einstein's view began to flow, where time and space mean different things to different observers. Without the absoluteness of Newton's time, there is no universally agreed now, and the relative nature of time means that observers disagree on how much time has passed. Einstein immediately realized that this doomed a cherished idea, the idea of synchronicity. This is the notion that two events at two different locations happen at exactly the same time. We experience this every day. It is part of the rhythm of life, where things happen at certain times. But this is all an illusion. And to understand this, let's take a look at one of Einstein's thought experiments. Consider 3 people riding in a speeding train carriage. One person stands at the back of the carriage, one at the front, and one in the middle. As the train trundles along at uniform speed, these 3 people decide to do an experiment. The person in the middle of the carriage has equipment that will release a pulse of light. That pulse of light will travel to the back and the front of the carriage. At either end of the carriage, each person has a mirror that reflects the pulse back towards the middle, and at the instant the light is reflected, the person at either end raises their hands in the air. Of course, in any practical train carriage, this experiment would be over in a moment, and the sluggish reaction time of the people would be the limiting factor. But this is the beauty of thought experiments. We can ignore all these day-to-day limitations and just concentrate on the physics. Let's think about the situation on the train. Everything seems symmetrical, from the light pulse heading out and its reflection to the pulse being received back in the middle of the carriage and the experiment coming to an end. It seems reasonable to say that both hands were raised at the same time. It was synchronous. But let's now think about the view of an outside observer, not riding the train, but just standing on the platform. And for fun, let's make the train move very fast, close to the speed of light. Just what does this outside observer see as the train roars by and the experimenters experiment? Well, this is where it gets a little odd. Our outside observer sees the experiment begin and the pulses of light heading along the carriage. But remember what Einstein's special relativity demands, that all observers see light travel at exactly the same speed, the speed of light. What influence does this have on what our observer sees? As the train is moving, the back of the carriage is reducing the distance that the light has to travel, while the front of the carriage is moving away, increasing the distance to the reflecting mirror. The light eventually bounces off each of the mirrors and makes its way back to the middle of the carriage. With the distances changing again, eventually both pulses make it back to the middle at the same instant. But when the outside observer is interrogated on what they saw, how would they describe the experiment? They will say that they saw the pulses emitted at the same time, and that they saw the pulses arrive back in the middle at the same time, but they saw the reflections and hands being raised at different times. Synchronicity depends on who is doing the observing. While Einstein was pleased with the special theory of relativity, he immediately spotted a problem, and that problem was gravity. Isaac Newton had given us his equations to describe gravity back in the 17th century, and these worked well in explaining the rate at which an apple falls from a tree or the orbit of the moon. Newton's equations, however, depended on the distance between masses. In Newton's universe, where time is absolute, we can talk about the separation at a precise now. But in Einstein's universe, where now is not universally defined, just which separation of the masses should we consider? Which now is now? This lack of synchronicity threw out the notion of a unique separation, and Einstein could find no way to shoehorn Newton's gravity into his relativity. So eventually, he had no choice but to reject Newton's gravity in its entirety. He had to go back to the drawing board and redefine gravity from the ground up. But where in his equations could gravity be included? The answer was even more bizarre than what had come before. Both time and space were malleable. Gravity could be encoded in the bending and stretching of the fabric of the cosmos. It took a decade of effort, but in 1915, Einstein had cracked the mathematics. It is this general theory of relativity that we use to describe the action of gravity today. No longer is gravity a force between two masses. Now, it is the curvature of spacetime. It is these mathematics that we use to describe the expanding universe, and even rely on in our daily lives to help run GPS. The conclusions of Einstein's relativity still hold across the cosmos. There is no synchronicity, no universally agreed now. Time and space can be immensely warped and distorted, and whether things exist at the same time is simply in the eye of the observer. And so now we can return to the remarkable quasar study from 2023. Did time really run slower when the universe was young? Well, if you were there, back in the infant cosmos, 1 second would feel like 1 second. But as the universe expands, the light that travels through it is stretched. This malleable, stretchy nature of space-time leads to what we observe in the distant cosmos being pulled thin across time. And so it seems to us that the distant past ticked by at a slower pace. And an even more extreme version of this concept is shown in the time dilation experienced around black holes. Space-time is warped to impossible extremes in the center of a black hole, but it is also warped and stretched as you get closer to the horizon. And so your experience of time slows down in comparison to distant observers. And bizarrely, these two ideas, time dilation around black holes and time dilation of the distant past, despite the vastly different contexts in which they arise, are effectively the same thing. And so, from the earliest decades of the 20th century, our vision of time was changed forever. In Einstein's revolutionary view of the universe, the passage of time is utterly personal. Your clock, be it mechanical like a watch or biological like the beat of your heart, ticks and talks at a regular 1 second per second. But other people's clocks can tick radically different relative to yours. If they are moving differently to you, if they sit somewhere differently to you in a different gravitational field, or if they are located in a different epoch of the life of the universe. This bending of time is part of the cosmos. The long-lived muons smashing into the surface of the Earth are testament to this, as are experiments where atomic clocks are taken for journeys around the Earth, ticking their own ticks so they are desynchronized when they are reunited. And we might even be able to use this relative nature of time to travel into the future. All we would need to do is hang out in the intense gravitational field of a black hole, a place where time, relative to the rest of the universe, effectively grinds to a halt. So whilst minutes or hours pass for you, when you emerge, years and decades will have passed outside. Pulling yourself away from the distant universe, you drag your attention back to the apple. You feel sure that the apple is here right now, no more than a couple of meters away. But you now have to accept that your now is precisely that. The now that belongs to you. Another way that your reality is yours, and yours alone. This thought makes you furrow your brow as the idea swirls in your mind. When and where reality is seems to be a slippery question, but what it is could perhaps be simpler. What is the world around you made of? How would you dismantle the universe? The atom split, huge force released. So screamed the headlines of the Melbourne Argus in May 1932. Cambridge achievement, success of British scientists. The nature of reality had been smashed into pieces. The headline was carried in a newspaper 20,000 kilometres from the laboratory in Cambridge, a testament to the earth-shattering nature of the discovery. A goal of ancient philosophers and seers had finally been achieved, for the British scientists, Ernest Walton and John Cockcroft, were modern-day alchemists. But instead of fire and brimstone, their laboratory gleamed with metal and wires. With electricity, magnetism and a beam of particles, they were able to transmute elements. Lithium was split into two new atoms, atoms of helium, their discovery showing that the world of the subatomic was now in the physicist's grasp. The question of just what matter is had been on the minds of philosophers for a long time. Some objects were clearly similar. Stones of various shapes and sizes were hard, while the solidness of stones contrasted with the squishiness of human flesh. They seem quite different, even fundamentally different, at their core. Philosophers had wondered if the stuff of nature was infinitely divisible, whether, like our apple, you could continue to slice it and dice it into smaller and smaller pieces. But ancient Greek and Indian thinkers had a new thought, that things are composed of ultimate pieces, tiny pieces we now know as atoms, from the Greek for uncuttable. To the ancient philosophers, these atoms were the fundamental pieces of reality. However, the notion that all things are made of atoms remained a philosophical musing for a few thousand years. But by the 18th century, scientific evidence for the physical existence of atoms was emerging, and not from the experimental laboratories of physicists, but from that of a botanist. The botanist in question was Robert Brown, born in Scotland in 1773. He had a distinguished career, travelling the world in the ship The Investigator to chart plant life. Many years later, in 1827, he was still studying the world of plants, but his focus was tiny grains of pollen. This pollen was floating on the surface of water, and Brown examined it under a microscope. But what Brown saw mystified him. Instead of sitting restfully on the water, he saw them dance and jiggle. Brown knew that pollen came from plants, so perhaps the jiggling was due to life in action, that the pollen grains were able to propel themselves through the liquid. But other materials, clearly dead material like chalk dust, showed the same kind of dance. This Brownian motion had nothing to do with life. Many people pondered the question of the jiggling pollen as seen by Brown, but the answer would not be found for another 7 decades, until 1905, arguably the most famous year in all of science. Albert Einstein's Annus Mirabilis. In this year of miracles, Einstein is generally remembered for one particular discovery, his special theory of relativity and all the weirdness of space and time that conveys. But it is also the year he revolutionized quantum physics through the photoelectric effect, and he finally explained the weird motion found by Robert Brown. Einstein's insight is as simple as it is brilliant. He realized that the jiggling of the pollen was not the pollen propelling itself, but being propelled by external forces, forces delivered by the collision of individual water molecules. But how can this possibly be? A pollen grain, whilst tiny, is a billion times heavier than a water molecule. How can the crash of a water molecule into pollen have any influence at all? Imagine you are at a truly massive rock concert, with music blasting from the stage. You are deep in the crowd, a crowd of tens of thousands of people. Now and again, the crowd surges to the left or right, front or back, and in these surges, all you can do is go with the crowd. Intermittently, the surges die away as you stand shoulder to shoulder with your fellow revelers. But the crowd is restless. You are jostled from all sides, a push from here and a push from there. Your body moves as you try to hold your space, but you slowly start to jiggle about due to the relentless pushes. These pushes are not even, sometimes more from the right, sometimes the left, sometimes front or back, with you unable to predict from where the next push will come. No matter what you do, your entire body moves a little this way and a little that way. Einstein realized that Brownian motion was precisely this kind of drunkard's walk. Every second, he said, an uncountable number of water molecules collide with a grain. The net result is that these fluctuations and collisions back and forth lead to the random jiggling, and the pollen grain dances along to the molecular tune. From his calculations, Einstein was able to calculate the size of the collisions and their fluctuations, confirming that water was comprised of an immense number of absolutely microscopic molecules. And so atomic hypothesis became atomic reality, and atoms appeared to be the building blocks of our world. And yet, just as their existence was proven, these indivisible atoms began to divide. It was in 1896 that Henri Becquerel and Marie Curie found that the world of the atom was unstable, and that some elements could transmute into others, spitting out other pieces as they did so. And in 1897, J.J. Thomson discovered the electron. It was clear that something was living inside the atoms that made up reality, and the race to split the atom and reveal its contents was on. For his discovery, Thomson was awarded a Nobel Prize in 1906, but it was his protege that was to truly reveal the structure of matter, the father of nuclear physics, Ernest Rutherford. In the first decade of the 20th century, Rutherford set two young men to probe the structure of matter. In a darkened room at the University of Manchester, they peered into inky blackness. They were looking for tiny flashes that indicated a collision as tiny pieces hit a fluorescent screen, and the results so far had been precisely as expected. The two men were Hans Geiger and Ernest Marsden. Geiger's name would be immortalized in the radiation detector named after him, but that still lay several years into his future. For now, he patiently stared into the darkness, logging each of the tiny flashes that he spied. The experiments continued, counting flash after flash, until one day Rutherford suggested that they look for flashes where none should be expected. So Geiger and Marsden dutifully modified their experiment and again stared into the darkness. And it was then they changed our understanding of physical reality forever. Rutherford was stunned, saying it was the most incredible event of his life. At 40 years old, he was still quite young, but had already been awarded a Nobel Prize for his work. But with this new experiment, the atomic world would never be the same again. But why? What had they seen? And what had it meant? Thomson's discovery of the electron had provided new clues to the structure of atoms. The electron clearly carried some negative electric charge, so inside the atom must be a mix of positive and negative charges, as overall they are neutral. The question was just how this charge was distributed. Thomson had proposed his model for the nature of the atom, something we now know as the plum pudding model. Confusingly, a plum pudding doesn't contain any plums, but it's actually a fruitcake with raisins, and the electrons, Thomson said, were just like these raisins, suspended in a positive mixture of cake. It was precisely this model of the atom that Rutherford was testing in his experiment. He created a beam of alpha particles, charged helium nuclei emitted from a radioactive source, and directed them to crash into a foil of gold. And it was the recoil of these collisions that Geiger and Marsden were looking for as they peered for flashes in the dark. As the alpha particles impacted the gold foil, many of them sailed right through, missing the gold atoms entirely. However, now and again, an alpha particle would crash directly into an individual gold atom. Rutherford surmised that these should feel the push and pull of the charges within the atom, and their paths would be deflected out of the beam. If Thomson was correct, and the atom was a general mix of positive and negative charges, then these deflections would be relatively modest, flung only slightly from the beam. And this is what Geiger and Marsden had spied as they sat in the darkness of their Manchester laboratory. But following Rutherford's suggestion, they also found alpha particles scattered far, far from the beam. Rutherford was astonished. For an alpha particle to be so radically scattered was simply impossible in Thomson's vision of the atom. Rutherford would go on to say, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." But the question remained, if Thomson's atom could not explain the scattering of alpha particles, what could? Rutherford concluded that instead of being spread out, the positive charge must be tightly concentrated, so that there is an immense electromagnetic repulsion between the atomic charge and the alpha particle, so immense in fact that the alpha particle can be flung in any direction. And this led to a rather confounding picture of just what an atom is. Rutherford knew that the electrons in the atom carried a negative charge. This charge must be broadly spread over the volume of the atom, spread so thinly that they barely influence the alpha particles. The electrons, however, carried very little mass. This meant that the totality of the mass must sit in the positive charge at the nucleus of the atom. But whilst massive, the nucleus is very small, tens of thousands of times smaller than the atom. And so with this, the vast majority of the volume of an atom became nothing but empty space. With Rutherford's insights, the startling Pandora's box of nuclear physics was open. Rutherford's atom fractures our view of reality, of the apparently solid nature of the world around you. Every chair, every wall, every tree, every apple is made of atoms, tied together into myriad molecules that define structure, color, and everything else. But it seems that this is nothing more than an illusion. Apples are made of water, vitamins, and butyl and hexyl acetate, the molecules responsible for their taste. But each atom in each molecule is really a cloud of electrons surrounding a minuscule nucleus, and the vast majority of each atom is nothing but empty space, so the apple is mostly empty space, and its solid appearance but an illusion. Of course, it's not only the apple, but everything that has the illusion of being solid. Everything, including yourself. This is disconcerting, but maybe you can try and comfort yourself with this image of yourself in reality. Maybe it's okay that atoms are mostly nothing but empty space. They're still made of something, with a nucleus and orbiting electrons. Surely those pieces are real. Surely those pieces are really there. But as they had with the molecule and atom before it, physicists would quickly realize that the mysterious nucleus of an atom was also far from fundamental. On the 10th of August 1915, a sniper found his target. His rifle trained on the enemy, he steadied his breathing and began to apply gentle pressure to the trigger. Birds scattered as the shot rang out. The sniper's aim was true and the enemy crumpled to the ground. The sniper moved on. There were plenty more to hunt. But little did he know that his bullet had snuffed out one of the greatest minds of the 20th century. World War I cost 20 million lives, both soldier and civilian, with many more wounded and injured. The failed Gallipoli campaign, seeking to weaken the Ottoman Empire, cost 100,000. Every life lost is a tragedy, a missing loved one whose potential goes unrealized. But this is particularly true of Henry G.J. Moseley. For before he joined up to be a soldier, something he did out of duty and against the wishes of his family, Moseley was a scientist who was unraveling the inner workings of the atom's nucleus. Born in 1887 in Dorset, England, the son of an Oxford professor, Moseley was a stellar student, studying at Oxford before joining Rutherford in Manchester in 1910. He had started to use X-rays to bombard different elements, with the hope of revealing the secrets of their atoms. As he did this, he had spied X-rays being emitted at different energies, and guessed something deep within the atom was causing them. There was also a pattern. In heavier elements, thought to contain heavier atoms, higher energy X-rays were emitted. In Holland, the amateur physicist Antonius Johannes van den Broek presented a bold idea. He knew that electrons, carrying the negative charge inside atoms, came in discrete chunks. Each electron appeared to have the same mass and the same charge. So what if the nucleus was the same, built of separate but positive charges? All atoms appear to be electrically neutral, so these positively charged chunks should exactly balance the negatively charged ones, and the only difference between the elements would be the number of positive charges in the nucleus, as this would set the number of orbiting electrons and dictate how the atom interacts with others. The simplest element would have one of these charges, the next two, and so on. And Moseley realized that this was the pattern he was seeing with his X-rays, and with this one insight, he rearranged the periodic table based on what we now know as the atomic number, still the form of the periodic table that we use today. Speaking in 1962, long after Moseley's untimely death, the giant of quantum mechanics Niels Bohr said, "You see, actually, the Rutherford work was not taken seriously. There was no mention of it in any place. The great change came from Moseley." And who knows what else Moseley would have contributed to science had he not been cut down by that sniper's bullet in 1915. Things moved quickly as the Great War ground towards its eventual end. It was again Rutherford, always at the forefront, who was deep in the discovery. And through his investigations into radioactivity, he finally uncovered the true nature of the atom. Hydrogen was the simplest element, just one piece of positive charge joined by one electron. whereas helium had 2 positive charges and 2 electrons. Then lithium with 3 of each, beryllium with 4, and so on and so on. Like the electron, each of these positive charges were identical, both in terms of the charge they carried and the mass they were made of. Rutherford named these positively charged, massive particles protons, and eventually, in 1932, after being theorized for years, the neutron was also identified in experiments. The makeup of the atom was complete. It had started off as a mess of complexity, becoming simplified through the realization that the world is built from 92 natural elements. But with the discovery of the proton, neutron, and electron, things became simpler still, with atoms of all the elements and their isotopes built of nothing but these 3 key pieces of reality. In the outer reaches of the atom roam the electrons, negatively charged tiny particles that whiz around at close to the speed of light. And at the very heart of the atom sits the nucleus, positively charged and comprised of protons and neutrons. It is the home to atomic mass. But as Rutherford's new view of atoms took hold, others realized it spelt doom for physics as they knew it. It contained a fatal flaw. There is, they said, no way an electron can remain in its orbit. Rutherford's version of the atom should not be able to exist at all. The problem came from James Clerk Maxwell's equations of electromagnetism. These demanded that an accelerating charge must radiate away its energy as electromagnetic waves, and as an orbiting electron is in a constant state of acceleration, it must constantly lose energy. It should spiral into oblivion in the nucleus of the atom. There was nothing in the physical laws of Newton or Maxwell that seemed to prevent this. Nothing in the laws of reality as we understood them could make matter stable. So physicists made a decision. They decided to change the rules, and in the process, change the nature of reality forever. In 1943, the father of quantum mechanics, Niels Bohr, found himself in a predicament. Germany had declared his family Jewish, and his arrest was imminent. So, with the help of the Dutch resistance, he fled to neutral Sweden. But his trials and tribulations were not over. For the British heard of his escape and decided they needed this quantum legend. The Second World War had been raging for 4 long years, and the Allies had decided that a new weapon, an atomic weapon, must be developed to end the carnage. Bohr's insights into the subatomic world would benefit them and stop the enemy from following the same path. Retrieved from Sweden and travelling in disguise as James Baker, Bohr eventually made his way to a secret town in New Mexico. And there, at Los Alamos, he contributed to the Manhattan Project and the building of the atomic bomb. Shyly, he always claimed that he wasn't really needed amongst the bright young minds, but project director Robert Oppenheimer disagreed. The early days of quantum mechanics were a heroic time. It was not the doing of any one man, it involved the collaboration of scores of scientists from many different lands. But from the first to the last, the deeply creative, subtle and critical spirit of Niels Bohr guided, restrained, deepened, and finally transmuted the enterprise. For 3 decades earlier, in 1913, as the world had been on the precipice of another world war, Bohr's mind had been focused not on how to unleash the power of the atom, but the question of why atoms existed at all. If Rutherford was right on the structure of the atom, then why didn't the electron simply spiral into the nucleus, just as the physical laws of Newton and Maxwell demanded? Revolution had been brewing for decades. By the close of the 19th century, physics had seemed pretty complete, except for a few niggles. Yet those niggles came to dominate and rewrite physics as we know it. And it all began with the question of why hot objects glow. Clearly, to make an object glow, you have to supply it with energy. This energy makes atoms vibrate, vibrations that generate light, the glow of a hot object. We know that an iron poker in a fire glows with a beautiful cherry red, and as we make it hotter, this red gives way to white and blue. But the question of why this particular choice of colours became the focus of a 42-year-old Max Planck, who combined the rules of established physics to understand how matter and light interacted. But his calculations failed time and time again, and as he reached a moment of absolute despair, he decided to rewrite the physics rulebook, as many had done before him and would do after, but never again with quite such far-reaching ramifications. Electromagnetic energy, he said, came in distinct packets of light. These discrete vibrations and light packets had to be quantized. And suddenly, Planck's strange new mathematics explained the glow of a hot poker. Planck thought all he had done was perform a little mathematical wizardry, but by 1905, Einstein also said that light comes in discrete chunks, quanta of energy, explaining how electrons are ejected from metal when under a light source. Suddenly, the quantized world was popping up everywhere. The quantum revolution was gathering pace as the subatomic world was laid bare. And it was Rutherford's insights that showed the atom itself would have to be quantized. But just what rules governed this quantized atom eluded him, and these answers came from Bohr. Electrons, said Bohr, were only allowed to exist in distinct orbits around a nucleus. These orbits are set by the momentum of the electron, and so each orbit has a specific energy. Electrons can move between orbits only if the exact energy difference is absorbed or emitted, and there would be the smallest orbit that brought the electron no closer to the nucleus. In demanding electrons could only exist in certain orbits with certain energies, Bohr had quantized and saved the atom from collapsing in on itself with only chunks of energy able to change the atomic state. This was a resounding success for Bohr, securing him the Nobel Prize in Physics in 1922, but physicists still scratched their heads as to why the atom was quantized. And this answer would come 2 years after Bohr received his prize in Sweden from a radical proposition by a French aristocrat and physicist named Louis de Broglie. He had been watching the quantum revolution unfold and was perplexed by the notion that light, which was a wave in classical electromagnetism, sometimes behaved like a particle, delivering its energy in a single punch. In this quantum world, thought de Broglie, why should matter not be subject to this duality? So he declared that an electron, which had been thought of as a distinct particle, also possessed wave-like properties in its existence. Just like light, de Broglie said, electrons can be refracted and can interfere. And it was Schrödinger who applied this to Bohr's atom, asking us to think of the wave of the electron as not at a precise point, but spread over the entirety of the orbit. And so Bohr's quantized atom finally made sense. The electrons were behaving as waves and could only have certain wavelengths. Today, the notion that quantum objects can be particles and waves is common knowledge. But in its time, de Broglie's ideas shook the foundation of physics to its core, and in 1929, de Broglie found himself in Sweden, receiving his own Nobel Prize. And so by the 1930s, it seemed that reality was all sewn up. The periodic table was built of just 3 particles, protons, neutrons, and electrons, bound together in different ways by the mathematical rules of electromagnetism and quantum mechanics. But even this neat picture rapidly started to unravel. In 1929, English physicist Paul Dirac had been focused on the equations of quantum mechanics. His goal was to make quantum consistent with the other great physics theory, Einstein's relativity. His new equations worked, but immediately Dirac was puzzled by what they told him, for as well as describing the behavior of electrons, something else was in the mathematics. The equations also described a positively charged electron, a positron, a particle that seemed to have no place in the orderly atomic world. Perhaps people thought it was nothing more than a mathematical oddity that has no place in reality, but by 1932 it was unmistakably found in particle experiments. But soon after the discovery of the positron, a much stranger particle appeared in the collisions, one that had even less of a place in the atomic world than the positron. It looked like an electron with the same electric charge except for one key difference. this new particle appeared to be 200 times as massive as the electron. And unlike the electron, this new particle, the muon, decayed in 2/millionths of a second. And so the big question was, why does the muon exist when it seems that it's not needed to build reality? Indeed, particle physicist Isidore Rabi quipped, "Who ordered that, as the muon made a mess of atomic neatness?" But its discovery was the start of a cascade, with many strange and differing particles popping out of experiments. And so into the 1960s, chaos reigned in the world of the subatomic until the next level of reality was laid bare in what became known as the Standard Model. It was realized that protons and neutrons and most other particles are not truly fundamental, but are made of even smaller pieces, known as quarks. We now know that there are 6 kinds of quarks, grouped into 3 families. The lowest mass quarks are known as up and down, then charm and strange. Most massive of all are top and bottom, and the vast array of particles spat out in experiments are combinations of these quarks. Protons and neutrons are built from up and down quarks. Protons are 2 ups and a down, while neutrons are 2 downs and an up. 3 up quarks combine to form a delta++ particle, whereas a D+ is a charm quark combined with an anti-down quark. As well as the quarks, there are also the leptons, the electron and the muon, and the even more massive tauon, plus ghostly companions known as neutrinos, 1 for each kind of electron. So, the majority of reality we experience is a combination of electrons and up and down quarks. There are a few other pieces to the Standard Model, and we'll meet those soon, but it's important to note that these fundamental pieces appear to have no size at all. These truly fundamental pieces of reality are point-like, so in a way, each of your protons and neutrons is effectively empty. At the subatomic scale, your atoms are even emptier than Rutherford found. Your brow furrows as you think again about the apple. Knowing that it is mostly empty space was disturbing enough, but at least the electron and the atomic nucleus seemed solid. In the quantum world, this is simply not the case. Everything we thought was a particle is not. Quantum matter shows wave-like properties spread out over space and not in any precise location or with precise properties. Your apple is nothing more than a mix of these bizarre waves, all combining to be the fruit you see. You squint at the apple as the question of quantum waves washes over your mind. Just what are these waves? And just what is doing the waving? Is this what reality is? Just a sea of subatomic waves? Imagine that you are in your kitchen, mixing ingredients to bake a cake. As you read through the recipe, you see that you need a couple of eggs, and so you head for the fridge. In the fridge door, the eggs are neatly arranged in lines, with some holes filled and some holes empty. You close the door and get back to your baking, thinking little of the remaining eggs. In your mind, there are certainties. When you open the fridge again, the eggs will still be there, occupying the same holes as before. How could it be any other way? But our modern understanding of reality suggests that the universe is actually much stranger. Instead of eggs, let's think of a collection of electrons similarly arranged in holes. With the arrival of quantum mechanics in the early 20th century, it was realized that electrons cannot be described by the rigid rules of the physics of Newton. Instead of exact positions and velocities, electrons were described by probabilities. We can only talk about the chance of finding an electron here or there, and if we observe an electron in a particular hole, it will have a probability of being in the other holes. So next time you check on the electron, it might have tunneled into a new hole, and all of the electrons might have switched places. And so why don't the eggs in your fridge similarly hop between the holes in your fridge door? They too are governed by the rules of quantum mechanics and so by probabilities. Well, in a sense, they do. For although the chance of an entire egg quantumly jumping between holes is extremely tiny, it is not zero. Though very unlikely, within the laws of physics, everything is possible in the quantum world. It is just a case of probability. The quantum revolution dominated the physics of the early 20th century. Great minds from around the globe turned their attention to the strange realm of the subatomic. But not everyone was pleased with what this revolution had to say, including perhaps the greatest scientist of them all, Albert Einstein. The problem started in 1926 in a paper by the physicist Max Born. A year earlier, Erwin Schrödinger published his eponymous equation. This allowed physicists to calculate the properties of de Broglie's matter waves. But Schrödinger still didn't know just what these waves were. Born, however, said that everything makes sense if you interpret the waves as waves of probability. The amplitude of this wave function tells you the chances of an electron being here or there, and as time ticks by, this wave function can wash back and forth as the probabilities for an electron being in a particular location change. This answered one of the questions that had been nagging physicists when considering quantum waves, because when they experimented on electrons, they would see precise dings in their equipment. They would detect individual electrons as distinct particles. So how could they also exist as quantum waves? To Born, the particles, like electrons, behave like waves as they travel from one place to another, but when they interact with your detector, the wave collapses and the electron is at a precise spot. Experimental evidence was quickly sought to see if this picture was correct, and it didn't take long to arrive. The experimental setup was similar to Young's famous double-slit experiment, where light was shone through two slits and showed the unmistakable patterns of interference. This demonstrated that light travelled as a wave, as you need waves to construct interference, and if quantum matter behaved like waves, it should show interference too. The idea was to fire a beam of electrons onto a target of nickel with a regular pattern of atoms. If the electrons were little bullets, we would expect them to randomly ricochet off the target atoms. However, the experimenters found that there were certain directions in which electrons preferred to recoil and other recoil paths they seemed to avoid. And this was the unmistakable pattern of interference. Places where waves added and strengthened, and others where the waves cancelled each other out. To help understand this, imagine you are a sharpshooter at the Olympics. Through your sights, you zero in on your target 100 meters away. You line up your crosshairs, take a deep breath and hold it. But as you think about your glory yet to come, your mind starts wandering. What if you were a sharpshooter in the quantum world? In the quantum world, the certainty of everyday physics melts away. Instead of exact locations and velocity, your bullet is now governed by the rules of quantum probability, and when you squeeze the trigger, the bullet emerges from the barrel as a quantum wave, spreading out in all directions like the ripples of water on a pond. This quantum wave travels quite differently to the zipping path of the bullet. Quantum waves can diffract around corners and can interfere with other quantum waves. Indeed, a spray of quantum bullets would not result in a grouping of holes in the target. Instead, a pattern of interference would emerge, with some bullets here and none there. This strange mix of wave-like and particle-like properties in the quantum world is known as a duality, and quite why we don't experience this in everyday life remains a mystery. Although physicists have been able to see the effect of quantum waves even on the scale of large molecules, many tens of atoms travelling together as a quantum wave and showing interference. And so, experiments showed, precisely as Born had suggested, that the waves of the electrons were combining and cancelling. But bizarrely, their detectors were counting just individual electrons arriving. Quantum objects were definitively travelling as waves, but interacting with detectors as particles. Indeed, as further proof, today we use this fact in our most powerful of microscopes. Instead of a beam of light, these focus a beam of electrons onto a target and use the wave properties of the beam to reveal details beyond that visible to light. Born received his Nobel Prize in 1954, 1 year before Einstein's death. But in the decades in between, Einstein had become a vocal critic of this probabilistic picture of nature, convinced as he was that it could not be the way that the universe actually worked. Whilst Einstein and Born were friends, they never saw eye to eye on reality. Einstein was horrified by probability sitting at the heart of our world. He felt that the universe must be deterministic at its heart. Though he accepted that quantum mechanics could be probabilistic, he believed that there was something deeper, something hidden beneath the quantum world that clung to determinism. Indeed, in a now iconic letter to Born, Einstein outlined his sentiment. "I, at any rate, am convinced that God is not playing at dice." By 1935, Einstein had fled his native Germany and arrived in the USA. And it was there he wrote about a paradox at the heart of quantum mechanics, a paradox he was convinced would demonstrate the absurdity of some of its big ideas. And this paradox, almost a century old, is still key to our modern understanding of the quantum world. It is known as the EPR paradox, after its authors Einstein, Podolsky and Rosen, and it highlighted one of Einstein's biggest problems with quantum mechanics, the apparently instantaneous collapse of the probability waves through observation into particles. And to understand its impact, let's start with thinking about two quantum particles. One of the interesting things about the wave function is that when we have two particles, the wave function for both is not simply the sum of the wave functions of the individual wave functions. No, a new wave function can be written that encapsulates the properties of the two particles, and it's this combined wave function that gave Einstein a headache. Imagine the two particles are brought into existence through some event. The details of the event are unimportant, but it results in the particles having linked quantum values. For example, imagine the particles are born with quantum spin, one spinning up, one spinning down. This way, the total spin is equal to 0, so spin has been conserved in their creation. Except the wave function does not contain definite information, just probabilities. So, each particle has a 50% chance of spinning upwards and a 50% chance of downwards. However, an important rule of the universe is that the total spin is conserved, so if you detect one spinning upwards, the other absolutely must be spinning downwards. In Einstein's thought experiment, you can imagine the particles separating after their creation and moving an immense distance apart, maybe several light years. They are traveling as probability waves, and you don't know the orientation of either particle's spin. Everything is still a mix of probability. This is quantum entanglement. But imagine one of the particles runs into a spin detector. With a loud beep, it registers the spin and the display reads spin upwards. You now know that the spin of the other particle is definitely spin downwards. The wave function must have collapsed into the definite states of the particles. But herein lies the problem. Just how does this pair of widely separated particles know that one has had its spin determined? Does the wave function, which is strung between the two particles, collapse instantaneously, possibly across light years? If it did, Einstein said, then this collapse would occur faster than the speed of light. And that, of course, was forbidden. Nothing in the universe can travel faster than the speed of light, under any circumstances. The solution, he claimed, is that quantum mechanics simply could not be complete, that underlying its apparently probabilistic facade lurked something else, something definite and certain that we simply hadn't found yet. These hidden variables would be solid and deterministic values precisely describing a situation, and it would be these hidden values that described the true nature of reality. The hunt for these hidden variables was on. Einstein and de Broglie put new ideas on the table, then eventually threw them in the bin. Others sought a solution to the EPR paradox, which brought determinism back to the heart of reality, but by the 1960s, all attempts were dashed by the insights of an Irish physicist in Switzerland. John Stuart Bell was born in Belfast in 1928. From a young age, he decided that he wanted to be a scientist, and in 1960 he found himself as a theoretical physicist working on the Swiss-French border at the recently formed European Organisation for Nuclear Research, or CERN for short. Bell contributed many things to physics and the understanding of reality, but he is probably best remembered for what is known as the Bell inequalities. His thought experiment was similar to that laid out in the EPR paradox, but with a subtle and insightful twist. Just like in the EPR paradox, we first make a pair of particles that are entangled in their wave function. Then we allow them to separate to a large distance where each encounters a detector. The detector can register spin up or spin down, but each can be oriented differently. But let's start by imagining the two detectors are perfectly aligned. As we've seen before, if one detector registers an up, the other must register a down. If the readings on one detector are up, down, 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 the other must read down, up, up. The readings are perfectly correlated. Bell's twist was to consider what would happen if the two detectors were not aligned. What if one was set to register up, down, and the other was twisted to measure left, right? This might sound like a strange thing to do, because if a particle is spinning either up or down, how could it register any spin, left or right? But if you were thinking like this, you are still considering the particles as classical things, as if they are truly solid balls that contain a definite direction of spin. But remember, they are not. They are purely quantum particles, and their spins are probabilistic. So there will be some probability of spin up-down, and some probability of spin left-right. Though thinking like this can start to bring on a headache, it is the way the microscopic world works. Bell started to wonder about the correlations of the outputs, with one detector reading up, down, up, and the other right, left, right. He was able to conclude that if these choices are being made by hidden variables, by definite quantities tied to each of the particles, a particular pattern of correlations should be seen. And if there are no hidden variables, so Einstein was wrong, a different pattern should emerge. And so the rush to test Bell's experiment was underway. And it wasn't long until the first results were on the table. Calcium atoms were excited in a hot oven, emitting two correlated photons as they cooled. These photons zipped out of the oven and into the physicists' detectors, who then compared the polarizations of the photons, the vibrational direction of the electric field. Bell said that if there were hidden variables defining the photons, specific correlations would be measured. But if there were not, and the photon's properties were spread over the quantum wave function, then a distinctly different set of correlations would be measured. The results were conclusive. There could be no variables. Reality was not a property of things, but was non-local, extended over the quantum waves. And as the many experiments undertaken ever since further confirmed this conclusion, Einstein's notion that the underlying universe was deterministic was quietly put to bed. And so, at this point, you might be wondering what all this means. This seems like a minor academic argument about some exotic quantum stuff in weird experiments. But the ramifications for reality are huge. Locality has always been a key concept in physics. What it means is that something responds purely to its local environment. Proximity is important. A mass responds directly to a force acting upon it, but it doesn't know or care about a force acting on another mass far away. Indeed, it is the non-local nature of quantum mechanics that Einstein objected to, that a particle detection in one part of the universe can influence the properties of another elsewhere. In a letter to Max Born in 1947, Einstein referred to this as spukhafte Fernwirkungen, spooky action at a distance. And this was a step too far for Einstein's view of the universe. For what this means when extrapolated is baffling. An electron is not simply an electron, and neither is any other fundamental particle in the universe. Particles must be entangled with others, sharing their experiences across the cosmos. No individual thing is simply a thing. Everything universe-wide is truly connected. At this point, you might be sharing Einstein's feeling that this is a step too far, that there's no way your apple is entangled with other particles in the cosmos. But we have to remember that the universe simply does not care about your feelings, your intuition, or what you can process in your brain. It refuses to behave in a way that you think is sensible. And the award of the 2022 Nobel Prize in Physics demonstrates this cosmic absurdity. The laureates were Alan Aspect, John Clauser, and Anton Zeilinger, and the subject was entangled photons. Experimenting over decades, these physicists showed that widely separate particles behave as one, and their goal was to dismiss any prospect of there being any hidden variables defining reality. A recent example of these experiments, the cosmic Bell test, might be the most extreme. The worry was that experiments to reveal Bell's correlations might not be quite telling us the truth. Experiments are built of atoms, and what if all these particles had interacted through their long histories? And worse than that, the experimenters themselves were made of similarly entangled particles too. When physicists set up their experiments, they like to think that they are distinctly separate from them. They think that they are objective observers, just looking at the outcomes of the laws of physics. The equipment in their lab is, in their minds, effectively isolated from the rest of the universe, and what they see is just the outcome of the physics in front of them. However, this is not quite the case, for the experimental apparatus is made of atoms. Atoms that have a history much older than the experiment itself. The physicists are also made of atoms with a history much older than them. Atoms that have been around for billions and billions of years. And so over these billions of years, there have been countless opportunities for these atoms to tangle. And in these interactions, any hidden variables could have been rewritten and correlated. This would mean that the correlations the physicists measure could simply be a result of the atom's long history, rather than the physics being non-local. This had the potential to introduce quantum loopholes into the experiment, and physicists wondered if hidden variables were colluding to make it look like they didn't exist. They needed to set the settings of their experiment in a way that could not be influenced by earthly ways. And so, they looked to the skies. They set up their experiment as usual, and then they brought in the light of two distant stars. The starlight fluctuated slightly, and these fluctuations became part of the experiment. These flutterings were used to set the orientations at which the spins were measured. And again, the experiment revealed that reality must be non-local. Remarkably, these experiments were even repeated using cosmological quasars rather than stars, pushing the possibility of a hidden variable loophole occurring back almost 8 billion years to the time of these extremely bright galaxies. Again, the spins of the particles were explored at orientations set by the fluctuating light of the quasars. And again, the results were unequivocal. Reality must be non-local. It is not simply there. Again, you look over and spy your apple. And again, you begin to wonder. Your mind can handle the fact that your apple is, at heart, a collection of fundamental particles, and it feels sensible that they are there, part of the fruit you can see. But these particles are entangled with each other and with others in the universe, and it seems that the apple is actually spookily entwined with the cosmos. And so now, the question is, why? Why exactly is this apple and this universe so connected? What are the rules that run beneath everything? On the 18th of April, 1955, the old man died. He was born in Germany almost 8 decades earlier, but his last moments were in an American hospital. His final words were in his native tongue, but these are lost to posterity, as the nurse who was caring for him was unfamiliar with the German language. But in the hours before his death, the man had asked for 3 things: his glasses, his writing equipment, and his equations, to work on one final problem. This man, Albert Einstein, is considered one of the greatest physicists of all time, and his name is splashed across the pages of the textbooks of modern physics. But later in his life, his work had become focused on a single question, a question that still haunts physicists today. 2 central theories emerged from the revolution of the first decades of the 20th century. We've met them both in our story so far. Einstein's relativity described the actions of gravity across the cosmos, while quantum mechanics explained the universe of the subatomic. Quantum mechanics was refined throughout the 20th century, evolving into what we now know as quantum field theory. It is these fields that contain the rippling waves of probability in quantum mechanics, and it is these fields that describe the physics of the fundamental pieces, like electrons and quarks. We've also already encountered the standard model of particle physics, and this is really a theory about the interaction of these quantum fields. When 2 charged particles, like electrons, interact, they create vibrations in the electromagnetic field. And these vibrations, the carriers of the electromagnetic force, are the photons. And of course, the electrons themselves are also vibrations in the electron field, just as each type of quark that makes up neutrons and protons are vibrations in their own quark fields, and so on for other particles. There are also other fields for other fundamental forces. The strong force is responsible for holding the quarks in protons and neutrons together, and for binding these particles in the nuclei of atoms. Vibrations in the strong field are the gluons, carriers of the strong force. There are also fields associated with the weak force, responsible for aspects of radioactivity, and their vibrations correspond to what are known as the W and Z bosons. For every force, there is a vibration in a field, and that vibration is a quantum particle. To understand this, let's take a look at the life of a neutron. Left on its own, a free neutron will decay in about 15 minutes, transforming into a proton and spitting out an electron and a ghostly neutrino. But just what is happening in terms of the quantum fields? We have to remember that a neutron is a collection of 3 quarks, 2 down quarks and an up quark. These quarks are constantly generating vibrations in the strong field, with gluons flying about and binding the neutron. But the weak field is still there, and eventually one of the quarks will pluck a new vibration in it. This will cause one of the down quarks to transform into an up quark, turning the neutron into a proton. The ripple in the weak field represents a W- boson and flies away from the newly formed proton. But this particle lives for only a very short time, less than a billionth of a second. As its vibration vanishes, it produces vibrations in new fields, creating an electron and neutrino. And all quantum particle interactions can be described in exactly the same way. But one other quantum field is necessary to round off the picture. Perhaps the most famous quantum field of all, the Higgs field. Interactions with the Higgs field give mass to the fundamental particles. The vibrations represent the Higgs boson, discovered in 2012 after a 4-decade search. It was in the early 1960s that physicists realized that there was a problem. As we know, the weak force has two associated particles, bosons known as the W and Z. Quantum field theory requires force particles to be massless. For electromagnetism, the force particle is the photon, a massless particle, and for the strong force, the force particle is the gluon, again a massless particle. And so why, physicists asked, did the W and Z of the weak force have mass? Simply adding mass to the W and Z in the equations proved a disaster, as quickly the mathematical terms exploded to infinities. So it was clear a new mechanism would be needed to add mass to the W and Z, and this mechanism was provided by the Higgs field, a field of energy that permeates all of space. The W and Z particles feel the presence of the Higgs field, coupling through a quantum interaction, whilst the photon and the gluon don't see the Higgs field at all. The problems of the masses of the W and Z bosons was solved, but it was realized that the Higgs mechanism had more up its sleeve. It was quickly seen that the mechanism that gave the weak force particles their mass could give mass to all the fundamental particles, to all the electrons and quarks, as these particles traveled through the seeming emptiness of space, the presence of the Higgs field ensuring they have just the right mass. Quantum field theory is highly successful, accurately predicting what is spat out of particle experiments. Electrons, quarks, sprays of gluons, and many other wonders can be found in its mathematics. Einstein's relativity is equally successful, predicting the motions of the objects in the heavens. But it is this superb accuracy of both these theories where Einstein's headaches began. While Einstein did not have the details of the fundamental forces available today, he did realize the problem in the language of the two theories. Relativity described gravity in terms of curved and warped spacetime. Quantum field theory, on the other hand, spoke about probability and waves. These two languages were completely at odds with each other, and you might wonder, so what? Does it really matter if we need two sets of mathematics? But to physicists like Einstein, this flew in the face of the dream of modern physics, the dream of unification. It all started with James Clerk Maxwell and his work on electromagnetism. In one set of equations, he showed that the two disparate phenomena, electricity and magnetism, are just two sides of the same coin. With the advent of the quantum field theory, things became simpler again. Three of the fundamental forces, electromagnetism, strong and weak, could be written in its language. One mathematical formalism to encompass seemingly diverse phenomena. It all worked so well. Except for gravity. Gravity simply did not fit. And so soon after the appearance of general relativity, physicists wondered if extra dimensions were the answer. What if spacetime had more dimensions and these contained the electromagnetic force? These ideas appeared to sort of work, but very imperfectly, and of course left a big question, namely, where are these extra dimensions? Surely we would notice if there was more than up-down, left-right and back-front in space. But physicists offered a novel solution. What if these dimensions were curled up tightly? So tightly, in fact, that we could have no experience of their existence, no way to resolve them, like using boxing gloves to put together Lego. Reality, some thought, could be built from a large number of these curled-up dimensions. These ideas languished for several decades, but in the 1960s saw a rebirth. Physicists realized that these curled-up dimensions could encompass all of the forces, but only if we treat fundamental particles as loops of string instead of points. The string theory revolution had begun. Into the 1980s and 90s, physicists were sure that they were on the right path. Any day, someone could crack the formidable mathematics and everything would fall into place. But as they toiled in the more than 20 dimensions needed for their theory, the fog of physics refused to lift, and unification seemed as distant as ever. More recently, string theory has morphed into M theory, the M in the title left open by its originator Edward Witten for when whatever M-theory truly is reveals itself. Strings have been replaced with membranes, so that might be the answer. But in reality, it is a loose collection of mathematical ideas, themselves looking for unification. Not everyone has been bitten by the string theory bug, and others have hunted for mathematical structures that could underpin reality. Loop quantum gravity is one such idea, knitting reality from fundamental chunks of space and time. But it too has proven mathematically challenging and is yet to prove itself as the unifying theory. But physicists are resilient, and the hunt for the ultimate theory of everything continues. New mathematical ideas are proposed and tested before usually being rejected. And to guide this search, physicists rely on one of the key concepts in physics, a concept that comes as close to the ultimate rule of the universe as anything else does: the idea of symmetry. We all have a passing notion of symmetry, things like a vase or a building being pleasing to the eye. But you can also use mathematics to talk about symmetries, and the existence of these symmetries has a profound impact on the nature of our reality. Take, for example, a sphere, a shape we can define precisely in mathematics. If we rotate a sphere, it still looks like a sphere. The sphere has rotational symmetry, a change that does not alter its appearance, and we can explore the mathematics of physics to search for similar symmetries. Because, as Emmy Noether showed in 1915, every symmetry implies a conservation law. But what does this mean? Imagine you have a physics experiment, something like rolling balls down a slope, and imagine you spend a while rolling balls and measuring their speeds. Now imagine that you move your physics experiment by a meter left or right and repeat the rolling. Would you expect the outcome to be the same or different? Surely it would be the same. So moving the experiment doesn't change the outcome. And this is a symmetry. But what is the conserved quantity that this implies? The mathematics of Noether tells us that the conserved thing is momentum. This property of motion, mass times velocity in Newton's theory, is conserved because of this symmetry. Momentum cannot simply disappear in a physical interaction, simply vanish. One billiard ball transfers its energy to another. Other symmetries exist and imply other conservation laws. If you rotate your experiment by 90 degrees and repeat the rolling of the balls, again, you expect the same outcome of your experiments. Now the conserved quantity is angular momentum, the conservation of spin in the universe. But perhaps the strangest symmetry is that associated with time. The fact that if you perform your experiment today and then tomorrow, you expect the same results. This time symmetry results in what seems like one of the most fundamental rules about the universe. This time symmetry implies the conservation of energy. Energy itself cannot be lost or created. Symmetries run deep through our ideas of theoretical physics. Einstein's special relativity is built entirely on symmetries, and it can be derived from what is known as the Lorentz group of symmetries. Indeed, it is these symmetries that demand that the speed of light is the fastest speed there is. But it is in quantum mechanics that symmetries truly reign supreme. It was realized that electromagnetism contained a symmetry, unexcitingly known as U1, and that other symmetry groups with more esoteric names described the strong and weak forces. With these symmetry groups came new conserved quantities. For electromagnetism, the quantity that is conserved is charge. But for the other forces, other quantum numbers appear, quantities that seem quite unfamiliar, things like isospin, lepton number, quark numbers, and a host of others. These all represent the rulebook of reality, defining what can and cannot happen. If the conservation laws hold, then interactions can occur. But if they are broken, interactions are strictly forbidden. Deep, deep down, reality appears to be built on symmetries. And so in the search for even deeper reality, physicists have tried to incorporate more and more symmetries. With supersymmetry, physicists try to hold a mirror up to the standard model, reflecting all existing fundamental particles with supersymmetric counterparts. So for electrons, there should also be selectrons. For photons, there should be photinos, and so on. Supersymmetry improves the mathematical elegance of the standard model, and for some it indicates the true path to enlightenment. But there has been no sign yet of any of the supersymmetric particles in any experiment. This, many claim, shows that supersymmetry as an idea is dead. Groups of symmetries also sit at the heart of string theories and M theories, and different symmetries are used to clean up and clarify loop quantum gravity. And so clues keep coming from geometry and symmetry, with many putting their faith in what is called the anti-de Sitter conformal field theory correspondence. This mouthful, usually abbreviated as ADS-CFT, was found by Argentinian Juan Maldacena in the late 90s. A mathematical mapping between aspects of string theory containing gravity and particle theories, it showed that the mathematics of one particular four-dimensional universe without gravity, a universe built on quantum mechanics alone, could match that of a five-dimensional universe with gravity. In short, that there was a clear mathematical link between the two, gravity and quantum mechanics. Immense effort has been placed in uncovering whether this correspondence tells us something deeper, perhaps a shadow of the true theory of everything that rules reality. However, the ADS-CFT correspondence could also have very bizarre implications. You might be familiar with the notion of an optical hologram, where a three-dimensional image is encoded in a two-dimensional space. One of the possible consequences of the ADS-CFT correspondence is that this may be the case for reality. What we experience as reality really just a projection of information stored in lower dimensions, and just like an optical hologram, nothing but an illusion conjured up from a two-dimensional plane. This notion, known as the holographic principle, grew out of our understanding of black holes. Black holes are extremely simple objects, completely described by only their mass, angular momentum, and charge. A black hole carries no memory of the objects that have ever fallen in. All information, other than those three properties, is seemingly forgotten. But in physics, it is generally accepted that information cannot be created or destroyed, only processed from one form of information to another. So for black holes, the question of just where all their information goes was problematic. Originally, it was suggested that the information is still there, encased in the black hole's heart. Here, it would just be hidden from the rest of the universe, out of sight and out of mind. But in the early 1970s, this picture was completely demolished, destroyed by the insights of a young physicist named Stephen Hawking. Hawking had wondered about the impact of quantum mechanics near a black hole. He eventually showed that the supposedly one-way influence of the event horizon, which allows things in but nothing out, conjured particles out of the foaming quantum background. These particles escaped into the universe, carrying energy with them. But from where did these particles' energy arise? Hawking's solution was astounding. He suggested that the energy was seemingly tapped from the mass of the black holes, and as the particles escaped, the mass of the black holes steadily decreases until it is completely evaporated away to nothing. But that wasn't the end. For if the black hole's information was written inside it, where did it go as the black hole evaporated? It didn't appear to be written onto the particles that were ejected, and physicists couldn't accept that the information had been erased. So they hunted for another solution. What if the information was not carried into the black hole, but instead was left elsewhere? Perhaps, they suggested, information was imprinted instead on the event horizon as things fell through. This information could then be etched onto the escaping particles as the black hole evaporates, with the total information released into the universe as the black hole completely disappeared. And so in this picture, the black hole is a three-dimensional object filling three-dimensional space, but it stores its information on a two-dimensional surface, the event horizon, in the same way that a hologram holds a three-dimensional image, all encoded into a two-dimensional surface. And some physicists have suggested the entire universe is structured the same way. Before we leave the importance of symmetry in physics, there is one more thing to explore, and that is the fact that the symmetries of our universe cannot be totally perfect. Some of the symmetries have to be imperfect, have to be cracked, for if they weren't, we would not be here. Take, for example, the asymmetry of matter in the cosmos. The universe appears to be stuffed with electrons, many orbiting atoms, some just floating out in space, but their antimatter counterparts, the positrons, are comparatively rare, extremely rare. In fact, within the Milky Way, scientists estimate that they make up no more than a quadrillionth of the amount of matter. And so, this raises the question, where are all the positrons? You might wonder why this is important, but it's really just another question of symmetry. Imagine the processes underway in the very early universe, at the time when matter was created. If the processes were purely symmetric, they would have made equal amounts of matter and antimatter. For every electron that was created, a corresponding positron would also be created. After the fiery birth of the Big Bang, these equal quantities of matter and antimatter would annihilate, and this complete annihilation would leave nothing behind but a featureless soup of radiation. With no matter, there would be no atoms, no stars, no planets, no people. The universe would simply settle down into a featureless nothing. So there must have been a break in the physics of matter creation, a tiny asymmetry of 1 part in a billion that left 1 electron for every billion annihilations, as well as protons rather than antiprotons and neutrons rather than antineutrons, leaving behind the matter from which we are made. Physicists are not quite sure where this crack is hidden in their theories, and perhaps they will need a theory of everything for this to finally be revealed. But other cracks in symmetry are apparent, and these might be providing clues to the ultimate nature of these asymmetries. The culprit is the weak force, the strangest member of the fundamental forces. Unlike the other forces, the weak force seems to distinguish between matter and antimatter. To understand this, let's start by thinking about a single hydrogen atom. This simplest of elements comprises a positively charged proton at its nucleus, which is orbited by a negatively charged electron. When this electron jumps in its orbit, it absorbs or emits a particular pattern of light. But what would happen if we considered instead an atom of antihydrogen? This would be a negatively charged antiproton orbited by a positively charged positron. When the positron jumps in its orbit, again a pattern of light is absorbed or emitted, and this pattern is precisely what is seen for normal hydrogen. This shows that electromagnetism is symmetric when considering matter and antimatter, and the same is true of the strong force and even gravity. But not the weak force. The weak force is not symmetrical. The outcome of reactions is different depending on whether they take place with matter or antimatter. And this is strangely tied to one of the universe's most mysterious particles, the neutrino. The neutrino only interacts via the weak force, so it's always a player in weak interaction. What makes the neutrino bizarre has something to do with one of its fundamental properties, and that is that all neutrinos spin the same way. This is a quantum property, and quantum spin comes in quantized amounts. They do not literally spin. Photons of light also possess spin, 1 unit of it in quantized amounts, and you can think of spin being right or left-handed as the photon travels. In our universe, we see both left-handed and right-handed photons, but the same is not true for neutrinos. All neutrinos are left-handed, whilst their antimatter cousins, antineutrinos, are right-handed, and this differentiates the interactions between matter and antimatter. But why do the neutrino and the weak force differentiate between left and right in the universe? Physicists still don't know the answer, but this crack in reality appears to have been essential for our very existence. Without it, everything would have been completely annihilated in the opening seconds of the cosmos. We have come a long way in this description of the rules of reality. We've discussed quantum fields and broken symmetries, warped spaces, and cracked symmetries. But there is one final example that shows how truly bizarre the quantum world really is when you follow its rules to the very end. Look up at the night sky. The light you see from distant stars is detected through electrons in your eyes, exchanging photons with electrons from millions of light years away. For two electrons to experience the electromagnetic force, they excite a vibration in the photon field. This photon travels between the two electrons, communicating force. But how do the electrons decide that they will exchange a photon and experience the electromagnetic force? You might think that one electron generates the photon vibration, which randomly impacts the other. However, this is not how quantum mathematics works. For the photon to be exchanged, the electrons have to agree, one to emit and one to receive. But how can they agree, as they only communicate through the speed of light, through photons? Looking at the mathematics, it all becomes a matter of interpretation. In what is known as the transactional interpretation, the electrons communicate, a handshake between the electrons that is part of the photon exchange. But to achieve this, the electrons exchange these handshakes through time. One electron sends its handshake into the future, the other into the past, and with a mutual agreement the photon is exchanged, even across billions of light years and one day, even trillions. But this need for time travel as a fundamental piece of reality is too much for some, who dismiss it as a mathematical convenience that masks something more fundamental. And so, where does this actually leave us in understanding reality? From holographic universes to wild mathematical implications, we now find ourselves at the philosophical edge of science, and what science even is. Is it a search for the truth, to uncover the ultimate nature of reality? Or is the best it can ever do is give us a mathematical approximation, a representation of a true reality that is forever hidden? Your thoughts race as your mind tries to process this complicated picture. But suddenly, your confusion is pushed aside as another thought snaps front and center in your mind. If nothing is real, then just what are you? Where do your thoughts reside? Where are you? There is an ancient Greek legend about the ship of Theseus. Over the centuries, time and travel takes its toll on the aging vessel, and constant maintenance and repair are needed to keep it afloat. Eventually, every plank and every nail, every string of thread and yard of sail has been replaced. Eventually, no original piece of the ship of Theseus remains. The philosophers of ancient Greece pondered whether this is still the ship of Theseus, and if it wasn't, when did Theseus's ship stop being Theseus's ship and become something else? It might seem that discussions about a legendary ship are little more than philosophical musings, but the ancient idea has some profound implications. Implications about the reality of you. How old are you? If you cut yourself, vividly red blood will flow from the wound. But is the blood that flows from your veins the same as when you were a child? Just how long does a red blood cell survive? Made deep in the dark marrow of our bones, a red blood cell lives a mere 4 months before it's broken down and excreted from the body. Every second, about 5 million red blood cells meet their ultimate demise, as freshly made cells flow into your bloodstream to replace them. Your body completely replaces your blood 3 times a year. Indeed, almost all of your body is eventually broken down and replaced. Your skin is replaced every few weeks, and for your internal organs, it might take a decade, but they too are eventually replaced, whereas your bones regenerate over about 15 years. You are literally not the person that you used to be. Every one of us, and all living creatures, are biological ships of Theseus. And so, are you still the same you that was born? Are you the same you, even though your individual cells have been replaced over and over? And like the ship of Theseus, if you are not the original you, when did this transition occur? And if you are not you, then just what are you? What makes you, you? The location of the mind, the seat of consciousness, has long been mysterious. To the ancient Egyptians, the heart was the center of all activity. It was home to the soul, with thoughts radiating out to the bodily extremities. This confusion was born out of a problem of thinking about thinking. Just what is a thought? Descartes decided that the brain and the mind must be separate things, coexisting and interacting within your head. And Gottfried Wilhelm Leibniz supported Descartes' view on the separation of brain and mind, asking you to imagine him shrunk smaller than the size of a flea. At this minute size, he then invited you to join him on a tour of the brain. As you wander around, there would be no sights of thoughts within the fleshy material, no ideas bubbling away inside all of the biological machinery. No, he said, the mind is something separate, something distinct from the brain. But with the coming of the 20th century, Descartes' dualism came under attack, for advances in technology and biological understanding began to look at the working brain. Real-time mapping revealed that Leibniz's fanciful journey might be blind to seeing thoughts, not due to anything mystical, but because thoughts, whilst apparently physical, are invisible to the naked eye. The secret to the mind was electricity. With sensitive mapping, it was discovered that the brain pulses and bursts with electrical activity, with certain sensations and feelings lighting up different parts of it. It was realized that the brain is a highly convoluted network, more than 80 billion neurons with myriad interconnections. Signals trigger new signals that flow throughout the network. Electrical activity surges and cycles, builds up and dies away. But though it might be satisfying to think that the mind is just messy electrical signals, many mysteries still remain as to just how it works. Where is thought? Where is love? Where is creativity and imagination? Just how the brain works is a puzzle, a clouded enigma. Indeed, even the great brain of Einstein was remarkable for being unremarkable, stolen from its skull in his autopsy. But focus has since grown on the complexity of the neural network inside our heads. Maybe consciousness and thought are a result of this complexity, an emergent phenomenon that can't simply be revealed by exploring the network. More than the sum of its parts. Emergent phenomena have often confused and bemused scientists. Indeed, emergent phenomena have often mystified many. There's a famous story of a Soviet aide visiting London in the 1980s, wanting to seek out the person who organizes the bread production in the city. In the Soviet system, bread production was centralized, with every step controlled. But in cities like Moscow, long queues at bread shops formed due to inefficiencies in the system. In the West, there was no bread czar managing production, yet an effective system had emerged from many, many workers performing their own tasks. It was reminiscent of an ant's nest. If you watch such a nest, many thousands of ants scurry about, seemingly with purpose. But no one ant controls the behavior of the colony. Instead, complex, emergent phenomena arise from each ant following a simple set of rules. Indeed, emergent phenomena can be found all across the physical world. Water is nothing but a collection of molecules attracting and repelling through electromagnetism. But a body of water can flow and bubble with turbulent eddies and swirls, emergent behavior from simple rules. The physical properties of matter and gases also emerge from simple rules, and some now wonder if these simple rules emerge from even more fundamental phenomena. Perhaps gravity emerges from truly fundamental pieces of space and time, in the same way that properties of water emerge from the interactions of molecules. And so, could it be true that the reality you experience, the world of wonders inside your head, is just the result of some complex wiring? Some find this conclusion unsettling, but for others, the notion gives them hope. If consciousness is just the result of complexity, not something beyond the physical domain, then maybe we have the hope of recreating, if not exceeding, consciousness. Indeed, this has been the goal of artificial intelligence for many decades, to build ever more complex networks, both virtual and physical, in the hope that intelligence emerges. There is a branch of physics known as synthetic intelligence that plans to put this to the test. This is unlike artificial intelligence, where people are trying to make computers think. Instead, in synthetic intelligence, physicists are building complex nanowire networks, wires that act like neurons and connections in our own minds. They hope that electric currents pulsing through these wires would represent electronic thoughts, and that these nanowires that have the ability to reorganize will have the ability to remember. This, of course, sounds like science fiction, but we might be only a few steps from the dream of thinking machines. Of course, for those who cling to Descartes' dualism, this is nothing but an empty quest, as for them, no physical mechanism could ever think in the way that humans do. But for the believers, it is all just a question of time and complexity, and one day their networks will become aware, become alive. But if consciousness is purely physical, then deeper philosophical questions begin to emerge. Are physical processes really playing out in fleshy pulp inside your skull? What if you are a brain in a vat being fed stimulation from a virtual reality? What if you are not a physical brain at all, but just software executing on a computer? And what if Descartes' dualism is right, and that consciousness truly exists beyond the physical world, a more ethereal plane where something like a soul resides? This opens another philosophical question, one that might be even more challenging for the idea of reality. Why should consciousness and thought be constrained to being human? What if it was much more widespread than that? What if consciousness is everywhere? It sounds again like we have entered the realm of science fiction, but this notion of a ubiquitous consciousness, of panpsychism, has been discussed by prominent philosophers. Consciousness that inhabits all corners of the universe, that everything, every particle is, in some sense, alive. People, trees, rocks, sand, dust, stars, galaxies, black holes, everything conscious. Molecules, atoms, protons, quarks and electrons, even the universe. This idea, whilst beloved by some philosophers, is too much for physicists to stomach. Philosophers tell them that it somehow links with the weirdness of quantum mechanics, but physicists simply feel that this is well beyond the bounds of what they class as science. And, as ever, both groups tend to ignore each other. And so, could everything be conscious? Is reality alive? Your scientific mind ponders on this for a moment, but concludes it a step too far. And so you turn your head and look over, once again, at the apple. It fills your focus as your brain processes all the aspects of reality that have crossed your mind. You wonder about the apple from its entirety to its fundamental pieces, and as you think about its existence and its reality, you wonder if the apple is contemplating yours? You start to ask yourself if your thoughts on reality could get any weirder. Of course they can. Picture a scientist. What image pops into your mind? For many, it will be the wild-haired Albert Einstein, late in life with a wrinkled face, perhaps with his tongue sticking out. Or maybe Isaac Newton in his formal regalia and 18th century wig. But these images are of the great scientists many years after their seminal works. The alleged comedy show The Big Bang Theory has shown us that science is a young person's game, and although the awkwardness that is played for laughs is an unhelpful scientific stereotype, it is correct that most scientists make their biggest breakthroughs when young. Indeed, it's important to remember that Einstein was only 26 during his miraculous year. Isaac Newton was also a young man when he had his greatest insights into nature, and in 1666, he was just 23. He'd already proved himself as precocious and had been studying at the University of Cambridge, but this year was to be a year like no other. The Black Death had returned again to Britain. The bubonic plague first raged across Europe in the 14th century, but it had never really gone away. For centuries, it resurged and cut a swathe through European populations. With its re-arrival in 1666, people had fled the cities for the relative safety of the countryside, and Isaac Newton left Cambridge for his family farm in the village of Woolsthorpe in Lincolnshire. As death stalked the land, Newton found solace under his famous apple tree, and his mind turned to unraveling the secrets of the universe. We've already met Newton's ideas of space and time, but let's look at time again. With his equations of motion, Newton could calculate how things changed with time, and time could be neatly cleaved into three distinct pieces: a past that had gone, a future that is yet to come, and an instant that is now. Reality, it appeared, existed at this unique instant of now, a precise and exact now, evolving from its state in the past to the present, and we can calculate what will happen on into the future. But Newton's equations are purely deterministic, and so if we had perfect knowledge at any time, we should be able to calculate the exact state of the universe at any other instant. And so this raises an interesting question. In a Newtonian universe, has the past really gone? Is the future really unknown and yet to come? In some sense, the realities of the past, present, and future all exist, and the instance of now is just sliding through this already complete history, with us just experiencing a moment of reality. This idea returned with a vengeance in Einstein's theory of relativity. Instead of just a background, space and time became central to the story, with each fundamental particle tracing out a distinct path, its world line, through these four dimensions. And like Newton, Einstein's universe is purely deterministic, with past, present, and future all existing. This came to be known as the block universe, and once again, the mathematics is pretty clear on something quite bizarre. The equations of relativity are unequivocal. Einstein's universe is a block universe. With perfect knowledge, there is no mystery about the future, as it can be calculated from now. In fact, Einstein's equations don't just define what now is, you have to define when now is. There is nothing special about now in Einstein's universe. Of course, the block universe raises some uncomfortable questions. Questions around free will. The ability to choose between possible options seems innately human, but in the block universe, this is just an illusion, as the future is already written. And the block universe also has even bigger consequences that stray back into science fiction. If the past and future are out there in the block universe, could we ever reach them? Out there, Da Vincian dinosaurs, every creature and everything that will ever be, and maybe there are convoluted spacetime paths that mean we can experience them in our now. But the issue is that the block universe just doesn't feel real. Surely the future is unknown and yet to come. And so many tried to look beyond the raw theories of Einstein to provide the answer. Eventually, the probabilistic nature of quantum mechanics appeared to show that Einstein could not be correct, the future being written from the possible outcomes of quantum questions. And so the picture that emerges from this compromise is that the universe is a block universe up to a point, and that point is now. Now is constantly being constructed as quantum questions are answered. Now adds another sheet of reality to the block universe, unfolding an unknown future in front of us, with the past solidified into the block behind us. And interestingly, this is the picture offered by loop quantum gravity, one of the contestants for the theory of everything. Within this theory, space and time are constantly being weaved from fundamental loops. Now is the edge of the weave, the past is the tapestry, and the future is the unknown ahead. Our reality, our now, would be at the busy edge of the construction of space and time. This gives you pause. Is the apple you see now the same apple you saw just a moment ago? Are its time, space, and fundamental constituents constantly being knitted from the ultimate fundamental? Are you and the apple being rewritten at every single instant you experience? Deconstruction after deconstruction, your grip on reality seems to be definitely slipping. And so you settle on a simpler question. Where is reality? Maybe reality is the block universe, and that's all there is. Maybe free will is an illusion. Or maybe loop quantum gravity is correct, and reality exists as an instant of an unfolding universe. But what if there is something much deeper underlying reality? Something that is not physical? What if, at the bottom, reality is nothing but numbers? This idea isn't as strange as you might expect. Indeed, it reflects our understanding of the workings of the fundamental universe. Written at the heart of all physical laws is the notion of information and information processing. Just what do the laws of physics do? Well, they take what we know about a particular situation, the information of that situation, such as the location and velocity of a ball flying through the air, and process it into information of that scenario into the future. This is probably most apparent in the rules of quantum mechanics, where the information of a scenario is encoded into the wave function. The rules of the quantum evolve the wave function, the information, into the future. Numbers are churned into new numbers as the laws of physics are played out. This all might sound a little esoteric, but by the mid-20th century, strong links had emerged between information and thermodynamics, as it was realized the effort to process a signal requires energy. A computer has to expend energy to flip a bit from a 1 to a 0 or vice versa, as does your brain as you process even the simplest of thoughts. And all of this has led some to propose that everything is really just information processing, that there is no fundamental difference between the processing of information on a computer or the processing of information in your mind, or the processing of physical information that underpins reality. This is the foundation of what is known as the simulation hypothesis. This hypothesis states that our thoughts, memories, and all our experiences are nothing but computations. This is deeper than the idea of a brain in a vat that we encountered previously, as there is no physical brain. In fact, in our reality, there would be nothing physical at all. Of course, the simulation hypothesis raises an immediate question. Just where would these computations be taking place? Perhaps they exist in a higher reality, a physical domain that we can know nothing about. But what would be the goals of our simulated reality? Why would our creators create us? What if we are little more than characters in a game of The Sims? But that's not all. What if the simulation was not created for us? What if it was constructed to explore other aspects of synthetic universes, and we are nothing but an unexpected side effect? What if the creators know nothing about our existence and care even less. Of course, we can argue about all these questions, for the answers might always elude us. But here on Earth, physicists do generate synthetic universes with the goal of understanding our reality, and also explore other seemingly hypothetical universes where the laws of physics are different. Maybe one day, with powerful enough computers, conscious creations may inhabit our synthetic worlds. But even if we are living in a simulated universe, and our reality is completely synthetic, surely our creators would inhabit a real reality, a physical reality. And so have we just pushed the problem upwards, or is it turtles all the way down? We come to this conclusion because we imagine that there must be a physical computer, a device that carries out the calculations that construct our reality and synthesize our universe. But what if there isn't? What if there is no physical basis for reality? What if there are only calculations? This is the idea of the mathematical universe. The lead proponent of the mathematical universe is Swedish-born Max Tegmark. In his earlier research, he focused on the challenges of modern cosmology, but eventually he turned his attention to some of the biggest questions we have. His mathematical universe is similar to that of a simulation hypothesis universe, but without the need for a physical computer to do the computations. And so, where would these calculations be performed? What would be performing them? Surely you need a computer to compute. But being truly fundamental means that these mathematics just exist, and there would be no real answer to where they came from or where they exist. Intriguingly, Tegmark's mathematical universe is actually a multiverse, containing not only our universe but all possible universes. In the growing maelstrom of mathematical calculations, there is not only our particular reality, but all possible realities, each defined by distinct mathematical structures of their own. Across this multiverse, there should be mathematics similar to our own, with multiple versions of you, whatever you really are, out there. Of course, there will be other universes which are quite different to our own, different in terms of the strengths of the fundamental forces or dimensions of space and time. The library of possible mathematics is immense, possibly infinite, and definitely much larger than the subset of mathematical structures we use to describe our cosmos. So out there, in the sea of fundamental mathematics, there could be much, much more. Not only universes that we've not dreamt of, but many we could never dream of. And one last horror, one prospect of reality exists in this mathematical universe, and it is tied to infinity. Every so often, within the infinite sea of calculations, just the right calculations will randomly come together. These calculations will look just like your mind, a mind filled with your memories and reality. In just an instant, you will be created, maybe considering an apple. Of course, to this brand new mind with all its memories, everything seems completely normal. They remember the big events from their lives and picking the apple from the tree. But the existence of this mind is only temporary, only a mathematical fluctuation. As quickly as the mathematical structure of this mind came into being, it vanishes back into the wash. This consciousness, with experiences of reality as real as ours, is doomed to disappear in an instant. And these relatively tiny fluctuations in the mathematics would massively outweigh the likelihood of our entire cosmos. And so, how do you know that you are not one of these minds that will vanish in a moment? How do you know that anything you think is real was there a moment ago? How do you know that you are not about to wink out of existence? By now you might be thinking, well, this is ridiculous. I know that I'm not a mathematical structure, and I remember what has happened to me. There's no chance that I'm a temporary existence. I know that I am truly real. But unfortunately, getting rid of the mathematical universe does not fix the problem. It is believed that our cosmos has an infinite amount of time ahead of us. and for this infinity, the universe is going to be cold and empty, long after the last star has died and the final black hole has evaporated into the background. And so it might seem that we would reach the end of the story of the universe, as not a lot will happen in our future empty cosmos. Surely it will be a quiet, uneventful place. But this future universe might not be as dead and buried as it might seem. And to understand this, we need to explore one of the most misunderstood concepts in physics: entropy. Ludwig Boltzmann was one of the most insightful minds of 19th century science. Before it was widely accepted, he was a supporter of the atomic hypothesis, the idea that at the smallest level matter is made of indivisible atoms, and he recast the laws of energy flow, thermodynamics, in terms of the motion of these indivisible atoms. Boltzmann's view attracted criticism from the scientific greats of his time, but shortly before his death in 1906, direct evidence for atoms began to appear. In pondering the realm of atoms, Boltzmann wondered how they could be arranged. Think about the air around you. Atoms of nitrogen, oxygen and carbon bound into myriad molecules. These molecules are whizzing about, colliding with each other, with the walls, and with you. At every moment, every configuration of atoms and molecules seems completely indistinguishable. But experience does tell us that the atoms are unlikely to spontaneously gather in one corner of the room. And if we started with all the atoms of air in one corner, they would rapidly spread out and fill the room. Boltzmann showed that this difference is simply a matter of statistics, that specific atomic configurations evolve into more general configurations. And this evolution of configurations from specific to general is known as the growth of entropy, and it has become one of the most fundamental rules in the cosmos. And these ideas of specific to general atomic configurations can be thought of another way, that order eventually gives way to disorder. Let's try to understand this in terms of energy. The total energy in any particular scenario must remain constant. This is another of the rules of thermodynamics. But not all energy is the same. Some of it is useful and some of it is not. The growth of entropy means that useful energy is degraded into useless energy. Imagine you have a cylinder of compressed air. This scenario is a little like the situation where you have all your air in the corner of the room. This highly specific case is said to have low entropy as it has lots of useful energy. And to tap this energy, all you have to do is open the valve. The rush of air from the valve can be used to spin a wheel, and this spinning wheel can be used to do some useful work, such as generate an electric current. But eventually, when all the pressures have equalized, the rush of air stops, the wheel stops spinning, and no more useful energy can be extracted. This is true of every physical process, with useful energy constantly degraded into useless energy. Indeed, your body is constantly fighting the growth of entropy, but to do so, you need a supply of concentrated energy from the food you eat, which you process into more useless energy in the form of waste and an infrared glow. You are doing your part in constantly increasing the entropy of the universe. Entropy has been rising since the dawn of time, with useful energy constantly diminishing, and the question of why the universe was born with extremely low entropy, so lots of useful energy, is still unanswered. But eventually, in the far distant future, there will be no useful energy left in the cosmos, and the universe will have entered the state of maximum entropy. And so, as we have seen before, it appears that we have reached the end of our story. For what can happen in this maximum entropy cosmos with no useful energy available? But remember, the rules of thermodynamics laid out by Boltzmann are statistical in nature, and in these statistics, bound by probabilities, even the seemingly impossible can eventually happen. Perhaps the air in your room could spontaneously gather into a single corner, or billiard balls could rearrange into their starting formation. Boltzmann said that whilst this is highly improbable, if we wait long enough, it must happen. How long might be a very long time, much longer than the current age of the universe, but if there is one thing the future cosmos will have in abundance, It is time. In the ultimate disordered state of the future universe, order will sometimes spontaneously arise. Every so often, the laws of thermodynamics and quantum mechanics will fluctuate. These fluctuations will in general bring some particles into being before they fluctuate away again, the universe going back to being quiet and uneventful. But even rarer than every so often, fluctuations will bring more substantial things into being. Vanishingly rarely, the complexity of a human mind will fluctuate into existence. Usually, these will be a blank slate, not thinking a single thought before vanishing again. But rarer still, a mind with memories and experiences will occur. These ethereal minds are known as Boltzmann brains and are extremely rare events, but with infinite time available, they will appear again and again and again. And over again, even your exact consciousness will pop into existence. Your consciousness, with all of your memories and experiences, an infinite number of times. And so, picking one of these at random, you are much more likely to be a Boltzmann's brain in a cold, dead universe than a physical, fleshy human enjoying a green, ripe apple. You, the mind watching this video, temporary. Your existence simply a fluctuation. In an instant, you will be gone. Are you sure that you have not just popped into existence and are about to disappear? Are you sure you are still here? Yes, at least for now. And so for one final time, your eyes settle on the solitary apple. The apple that sent you on this journey looking for the nature of reality. Your mind flashes across all the versions of reality you encountered in your dozing, from the forms of Plato through the weird world of quantum mechanics, across block universes, and in and out of holographic cosmoses. But clarity returns as your stomach starts to rumble. And again, you focus on the apple. You reach out and pick it up, feeling the smoothness of its skin in your hand. You take a bite. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.